Okay. Hello, my name is Artem. Unfortunately, Thomas wasn't able to present today, so I'm going to fill in. And today we're going to talk about symmetric memory keys. And before going there, let me recap on shared memories, because this is our target goal. Yeah. So SHMEM is an implementation of PGAS, parallel programming model. It has a standard API that targets portable and uniformly predictable results for OpenSHMEM programs. It is comprised of processing elements, which is in short called PE, and this PE name will appear on slides a lot. So please remember that it's not a rank, but it's the same meaning, basically. So typically PE is an operating system process that is communicating with the PEs are communicating with each other using OpenSHMEM primitives. And that's sort of similar to what MPI is defined from that perspective. So in the scope of this presentation, we are going to be mostly interested in memory model of the OpenSHMEM. So let's look at it a little bit closer. So an OpenSHMEM consists from the private data objects, which are typically local variables, but also I think you can use malloc, but I'm not sure about that, and remotely accessible symmetric data objects. So they are called symmetric data objects, and typically when you create the OpenSHMEM application, you're getting for granted all the global and static variables are included into that space, and also you can define the symmetric heap, and that symmetric heap will contain all the objects that are intended to be accessed via OpenSHMEM primitives. And you define the size of the symmetric heap upfront before launching the application, and then whenever you call SHMEM malloc, so malloc is a collective call, so it will it will require all the PEs to participate, and it will result in having a specific data buffer to appear in each heap, and that's why it's called symmetric. So every action of a PE with respect to this memory has to be mirrored on all of the PEs. And the in the basically cool outcome of that is that for symmetric data, each object, for example, variable X, is represented on all PEs with the same name, type, and size. And as I said, you can access, for example, from PE0, you can access variable X on PE1. And for that, you can just use the address, the local address of the variable X, and that will tell the runtime, explain enough to the runtime how to find variable X on any other PE. So in the primitive, you just specify the PE number that you are targeting, and that will be enough. So yeah, and symmetric objects are grouped in SHMEM segments. So now, what about symmetric memory keys? So this is the concept that I will explain a bit later, but here is the environment that we are targeting. So OpenSHMEM is sharing memory over multiple processes according to OpenSHMEM model, and it's using UCX, specifically UCP API, to perform data transfers, atomic operations. And we are relying on UCX, and the goal is to reduce the number of remote keys that we need to use in order to implement symmetric memory model that is being used in OpenSHMEM. That's the goal. So here, how on a lower level the OpenSHMEM symmetric memory looks like. So for a specific process, on a specific process, we have basically a set of data structures that describe each PE in the application. So each project needs to actually know everything about all other PEs in terms of how their memory is organized. So this is a low level thing. It's not visible, at the OpenSHMEM level, but this is something that we're trying to optimize. So here, for example, in this example, we have 3 segments that comprise the symmetric memory. And for each segment, it is described with the, so a segment is a virtually contiguous memory region. It is created simultaneously by all PEs. And typically we are talking about 3 to 5 segments in the application. Like a very typical case would be a global variables, then memory heap, and sometimes we have a device memory that's considered as a 3rd segment. So each segment needs to have a remote key. And as you increase number of PEs, of course, number of these data structures grows, and each R key occupying some memory. So we're trying to optimize this for with the symmetric memory key. So what is UCP remote key? So for so remote key contains a memory, 1 memory per memory domain, memory key per memory domain. And basically it is a list of remote keys for each transport that was discovered. And in addition, it has some meta information that is required for it. It doesn't really require it for the transport, but this is for UCX to better optimize the data path. So it can quicker, because UCX supports so many transport, and for specific endpoint, it may pre-calculate which is the best transport to be used, for example, and some other optimizations they can do upfront. And so this meta information is also associated with the remote key. And so if we consider OpenSHMEM case, we can try to optimize the size of the remote key on one hand, and on another hand, we can try to reduce the number of remote keys that we need. So for OpenSHMEM use case, we know that RDMA is used for internode communication. Most typically for UCX, it's InfiniBand. Then we have we are trying to leverage shared memory as much as possible for intranode communications. And what's also typical for OpenSHMEM applications is that HPC nodes are typically homogeneous. Okay, so given that, what can we do? So we can try to avoid storing extra information for such homogeneous systems, like deduplication of meta information, memory domains, endpoint configuration, some other stuff that I showed on the previous slide that is part of the R key. And also we can try to reduce the number of unique internode keys. So we are working on a feature for InfiniBand that allows to reduce the randomization of remote memory keys, which allows us to perform deduplication at the AB transport level. So shared memory keys are not so much of a concern, because usually the number of PEs that are accessible via shared memory does not scale very quickly. with the cluster scale. It's scales much slower. Okay, so what do we propose? So we propose multiple changes in the UCX API. Actually, very few. The first thing is we are introducing the memory map symmetric key R key flag that is being passed to UCP memory map. So that flag indicates that the memory is allocated for environments with like HPC environments with symmetric memory, and which means that we have a potential for deduplication. And the expectation is that UCX is going to do the best effort to support that. And if some transport does not support deduplication, it just continues to work as usual. But how we can take advantage of deduplication? In order to do that, we introduce a new API that works with every transport, but I will explain on the next slide a little bit more how it works. And this API allows us to compare R keys, unpacked R keys, and see if they're equal or not. And then what this API gives us for OpenSHMEM, for example, during the OpenSHMEM bootstrap, when the application is initialized, we perform the exchange of the R keys. This is this happens in SHMEM init, and then once we received all of the keys, we start populating some kind of a table. And during the population of the table, we actually compare the next R key being added to the table to the previously existing remote keys that are already added into that table. And we discard the keys, the latest key. If they are identical, we don't really use it. We start referencing the UCP R key that's already that's already in that table. So, and if the R key is completely unique, we just store it as a new item, as a new element. Hopefully, it will be referenced later. And the way it works for shared memory, it's always showing that the keys are different. So it never tells us that they're the same. And then if InfiniBand key, InfiniBand, when it is supported, then we are trying to show that our keys are same. And there is an additional field, the result of comparison, and that was Yossi's suggestion. I think very smart suggestion that we can, instead of just returning yes or no, equal or not, we can actually return three values. -1, which means that RQ1 is less than RQ2, +1, which means opposite, and 0, which means that R keys are equal. And what that gives us is during the deduplication procedure, when, as I mentioned, we need to compare each key to all the previously added keys, what we can do is we can use that value to implement a binary search, and that allows us to reduce the search time during the duplication for each element to be log2. And also the hope is that in the environment where this deduplication works, the number of keys will not be equal to number of PEs. So the expectation that n is actually going to be less than number of PEs. And as the outcome of that, on the left side we have the original implementation, and I marked with purple the PEs that are local to the PEN that's being depicted. and the greens are remote ones. So you can see that here we have to store everything. And on the right side, we have purple ones. They basically are the same. You store the same amount of data, but for the green ones, we actually reduce the size that is consumed by these PEs, because we have a standalone table that contains the ARCs themselves. And from this data structure, we just pointing to them in some way, which is defined by this ARCI compare result of the ARCI comparison. And I think ideal case is when we have just one ARCI for the segment. This is ideal case, which not really achievable at currently, but we're trying to achieve it, keep working to achieve that ideal case. This is our speed of light situation. And at the moment, we have just a few measurements that indicate the performance of the allocation. So we measure the time it takes to do the allocation. And as you can see, there is an impact when the number of processes per node starts growing and number of segments is quite high. However, I would consider this this case to be more typical than 30 segment case. So you can see that it takes about 1 to 2 milliseconds to create a segment. And the deduplication for us, that we observe that we can deduplicate like quite significantly, but at the moment we only worked on 3 nodes. So this is an ongoing work. And I guess that's it from my side. I guess I did it faster than 1 hour. I'm sorry for that. And I'm happy to answer the questions.
Hi, this is Radha Gargeya. And then I like this talk very much because we have an application where we use the ARCs, and currently the ARCI size is about 60, but I'm told that we can put an upper bound on it and it can grow in size and in later releases. And if you have many nodes and many processes, this makes it for an efficient memory usage. So I think this is a great feature. Just wanted to say thanks.
Thank you.
Good morning, everyone. My name is Christopher Taylor. I'm from Tactical Computing Labs, and today I'll be talking about extending OpenSHMEM's footprint to Rust-on-RISC-V, Python, NIM, and HPX. So that's kind of the order of things this morning. TCL is a research and development firm specializing in high-performance computing, compilers, runtime systems, scientific computing, modeling and simulations with a structural simulation toolkit, and we specialize in RISC-V hardware. First, we're going to talk a little bit about Rust work. We were able to get Rusty 2 and OpenSHMEM binding for Rust out of Stony Brook Labs, successfully running on RISC-V hardware. We went through and did the entire self-hosting, multi-stage bring up for a RISC-V-based Rust compiler, and all that worked perfectly. And then we successfully deployed O3S UCX under Rusty 2 on that hardware. So this is deployed on a Slurm cluster. We were able to successfully get InfiniBand support on RISC-V using ConnectX-3 and 4 cards, and more specifically, IP over IB. That particular interface worked perfectly. On the hardware side, we used Sci5, Hi5 unmatched development boards, and then to kind of validate the software works on different RISC-V hardware, we used Pine64, Star64 SBCs. a cluster of about 4 nodes with a workload manager. On to Python. So there's a compiler out there called Codon. It's an LLVM-based compiler for Python from a company called Exaloop. It compiles Python applications out to machine executable code. It supports Python C bindings. Pretty much everything you can compile, according to the documentation, because I haven't had an opportunity to test it all yet, you can compile pre-existing libraries into executables. It uses Bohem's garbage collection. Advanced developers can directly inline LLVM-IR into Python applications. And the foreign function interface only works for C because we're talking about LLVM's underlying infrastructure. This was a pre-Mojo technology. So for those of you that track these things, Mojo came out a couple months ago. It was a Latiner compiler that does something very similar. Codon's been around for about 2 or 3 years. It has an interesting licensing model. Every 2 years, the compiler ages off to an Apache 2 license from a proprietary license. So that's by release. OpenMP is natively supported by Codon, so Python users just have to drop an annotation on top of a loop, and they get OpenMP support for free. It provides support for static generics, which is particularly interesting. We're able to verify that that variables labeled static actually do get placed in the data segment, which is what you'd sort of expect in C. That means that they are now accessible to partition global address space. So we did a direct integration of OpenSHMEM into Python through this Codon compiler because of that LLVM foreign function interface. So we can do basic OpenSHMEM operations. And to kind of make a much more easy experience for users, we created 2 data types. One's called runtime, and one's called symmetric array. And that's a generic, so you can drop integers, floats, whatever you want in there. The runtime wrapper, again, provides really standard functionality for OpenSHMEM. And what sort of inspired this was standard scoped locks in C++. So the user would create a runtime object and then use Python with expressions and could put all their code under the with expression. So the runtime would initialize when it hits that scope, and then when it leaves that scope of the with expression, it would just finalize the runtime system. Symmetric arrays sort of fold in a lot of your standard OpenSHMEM operations and directly associate them with the data that is stored in the array, right? So I can do localized slices, copies, deep copies, puts, gets. I can do collective operations like max, min, sum, prod, all-to-all, and broadcast. All of that stuff works. And we validated that on both our RISC-V clusters. Here's an example of a very simple code. You can see where the runtime gets initialized as part of this with clause. And then whenever I want to get information about what's going on with the runtime, I just reference the variable and a method name, so it's fairly simplistic. NIM. So NIM's about 10 years old. Originally, it was called the Nimrod compiler or the Nimrod language. The syntax is very similar to Python. It compiles to C, C++, and a bunch of other programming language targets, but C and C++ are what we kind of care about here for performance. It boasts memory management features that are similar to Rust, so everything is sort of initialized constant by default, and you have to sort of tell it to mute, the variables are mutable in order to change their value or their state. It provides some really interesting metaprogramming features. Compile time logic can be manipulated using what they call a macro system, and so it kind of works a little bit like Rust in that when I define a macro at compile time, the macro gets access to the program syntax tree, and I can either create new subtrees of a user's AST. And in this particular case, we use that feature set to take variables that have been called symmetric variables and store them into the generated C program as static variables, so they end up in the data segment, and that gives them access to the global address space. We had to use symmetric as the keyword because static has a different semantic meaning in the language, because the language doesn't really have a concept of static variables in like a C or C++ concept. What is kind of interesting about NIM as a language is that templates and generic support are very similar to C++ in that users can create sets of types. So it's similar to sort of like a cross between a type def and a std variant from C++. So I can have like a type called some number, and it contains a set of different integer types that all represent numbers. So we kind of took the work that we did on the code on Python binding and sort of mapped it into this language just to see what would happen. So you get a lot of convenience functions and data types all kind of reflect what was done in the previous presentation or previous slide about Python. We provided direct bindings to OpenSHMEM. We made heavy use of the macro and templating system to pull this off. And all the output code gets generated to C, and then we kind of went through and did a validation of what code got generated by the compiler to make sure variables ended up in the right place. And by place, I mean the data segment or on the symmetric heap. Everything worked perfectly. So users can create symmetric variables, scalars, and arrays. A symmetric array would be, you know ahead of, so we've got two forms of symmetric arrays, right? Like one where you know how many elements are in it ahead of time, and then one where you have to compute it dynamically by making schmalloc calls. And we got both those types of things handled in the implementation. Okay. So arrays implement NIM's sequence interface. So you can use a symmetric array just like you can use any type of sequence type in NIM. And it also supports all the same functionality that we had done in Python all over again. One of the things we really want to do is kind of go back and see what the performance differentials are. But we didn't really have time to do that kind of work prior to this particular conference, which is unfortunate, but might be something we do soon in the future. Here's an example of the code, and to kind of highlight something, you'll see there's a symmetric main with a colon after it. This is a NIM macro, and this initializes the compile time logic that goes through and says, oh, you have a symmetric integer named Apple, so what we're going to do is store that in the data segment. Oh, we've got a symmetric sized array. We're gonna put that in the data segment, and then down here you can do your standard dynamic allocations on the symmetric heap with the new sim array, and you can see how all that stuff works. What is kind of interesting is that over here you'll see there's a min op, that's a minimization, minimum operation, and attached to it is a method called reduce, and that does about what you would expect, but I could flip these around. I could actually have B be placed here. There's a lot of like syntactic games you can sort of play with this pattern. NIM has a very unique way of allowing users the ability to sort of move variables around in the variable argument list and drop them in place of the target object that a method is being invoked on. I thought that was kind of interesting when we went through it. So you can just call min here and you get the same effect as you would get up here. Hopefully people watching can see my hands moving around. If not, I apologize to the audience. HPX, this is from Stellar Group. They're based at LSU. Some folks that participate in the runtime systems development are at the Swiss Supercomputing Center. And it's an asynchronous many-task runtime system. It implements the ISO C++ standard for data parallelism and concurrency. They've implemented std async, and they've mapped all that under their own namespace. They support coroutines currently, which is a new feature in language. And all their threads are user land based. You get 64K stacks, and HPX scales exceptionally well to very large problem sizes. Some additional features. Apex is a performance counter auto-tuning library that wraps active harmony, and that can be integrated into the runtime system. And so you can get this very unique way of, or pardon, introspection to what your user land threads are doing when you construct your task graphs with asynchronous calls. The communication subsystem for HPX is called Parcel Port. That manages all of the distributed communications between, they're called localities. Localities are the same as a rank or a P in the SHMEM model or in the MPI model. Altogether, you end up with distributed container support for something called an asynchronous global address space, where objects can sort of move around based on workload and currently what's going on in the underlying hardware. Think of it a little bit as, and this might be going way, way back for some folks. Corbub without any of the IDL language stuff that goes with it, right? It's just raw C++. You just write C++ and this all works without any of that ORB stuff from back in the day. So parcel port, as we saw yesterday, is implemented using MPI, libfabric, sockets, and LCI. This past year, we added in GasNet and OpenSHMEM support, and you can now AGAS over PGAS. OpenSHMEM's PE model maps directly into HPX's localities, so there wasn't any kind of issue making the mapping from one to the other. The parcel ports creates shared memory segments on each locality for all localities. And this model we sort of took from looking at the Chapel runtime system's use of GasNet. So for 4 locality, each locality gets 4 shared segments, 1 for itself and 1 for all the other localities. The shared segments operate as communication lanes. So puts and gets operate on those lanes to minimize contention between localities. And the runtime system actually does a fairly good job of managing situations where where you would kind of expect one locality to write into another locality. It handles all that reader-writer issues. The active message support was mostly lifted or modified versions of what was in the Chapel runtime system. And after kind of going through the process of doing the GasNet implementation, it became really clear that doing an OpenSHMEM implementation would be trivial. So went ahead and did that. The OpenSHMEM parcel port works similar to the GasNet one, but it depends. The key dependency was in the put signal functionality that's provided in OpenSHMEM, which I believe decomposes into a put and a put atomic. Those of you who are experts in OpenSHMEM can feel free to correct me at the end of the presentation. Put signal, that's the sauce, right? That's the sauce that made all this work. So here's an example. You can see the shared segments between localities. The first one's shared segment 0. Of course, that one maps to locality 0. And we have shared segment 1, which maps to locality 1. So when locality 0 wants to put data to locality 1, it writes to shared segment 1. And then locality 1 does the read. When the communication hits the remote locality, it goes through the work queue, and then the read happens. And then from locality 1 to locality 0, it just writes to shared segment 0. It's a fairly simplistic model. So that kind of summarizes the work we did extending OpenSHMEM and GasNet into different places. Does anyone have any questions? And I probably went through that really fast, which means we have a lot of time, right?
Yeah.
It's unfortunate.
Super fast. You would have to do now stand-up show or something.
Oh, stamp show? Okay. Anyone got like a top hat and a can and get some tap shoes? And
Any questions on?
does put signal just decompose down to a put plus a put atomic? Is it really that simple? Put signal. So to get the HPX support working, we use put signal. And I was under the impression that just decomposes these 2 operations as like a wrapper. Does that sound? Is that consistent?
You was the third person asking for.
Ooh,
That's
mean.
In the last 3 days.
I have a related question. Do you plan to have a native UCX implementation instead of OpenSHMEM?
Say that. I'm sorry.
Do you plan to have a native UCX implementation of top of the UCP API?
Yeah, I'd like to do that.
Because if we add something like put with atomic to UCP API, that doesn't necessarily mean it would be there in OpenSHMEM, because it has to pass also OpenSHMEM specification.
Okay. Yeah, the thing I wanted to bring up is that all of this we've tested with UCX as the underlying communication substrate for GasNet and for OpenSHMEM. My apologies for not bringing it up earlier.
Performance between them?
What's that?
Did you see any difference in performance between?
I haven't had a chance to performance test it. I'm sorry. We're kind of hoping to get in touch with the folks in the LCI group to see if we can maybe do like a bake-off, some performance characterizations between all these different communication layers.
And did you see any difference in semantics that example, between OpenSHMEM and GasNet, something that didn't work quite well?
They so GasNet was interesting in that you had to pre-register all the functionality ahead of time into a lookup table.
Yeah.
So when the messages hit, they just get I guess the GasNet queue looks up the table and says, "Oh, this message is a receive or a send." That was a considerable amount of code that had to get written compared to OpenSHMEM, where it was fairly straightforward. It looked a lot like the MPI code, quite frankly.
So which was a better fit, OpenSHMEM or GasNet?
Better in terms of performance or just in programming?
Maybe where did you have to write less code in order?
Oh, OpenSHMEM was a lot less code for sure. Yeah, but we were also using the previous. We weren't using GasNet X, so I haven't had an opportunity to take a look at that API yet and how that works. I'm going to assume it's similar. Is that fair to say?
I guess in Texas where you have the full remote access operations, right?
Yeah. Anyone else have any other questions? I haven't. I've posted. So this code is actually in 2 PRs. We're kind of dealing with some changes to the CI system. So both these parcel ports should be done in the next month or two. The GasNet code, the GasNet parcel port is already in HPX. We found some issues, some edge cases with the builds that we've been trying to get that resolved. The code on code, I'm pretty sure is not online yet. So if anyone wants that, please contact me. And the NIM OpenSHMEM stuff is available publicly on my GitHub repository. And if you want access to it, just look me up or contact me. And the Rust code, all that stuff still exists. I think the O3S folks, the Open Source Software Solutions Group, they're maintaining all that code. So yeah, that's about it. Sir.
So you kind of inspected multiple languages. Were these all project-driven, like different projects that were already written in these languages?
Nope.
Or did you have?
Just had a wild.
You had free choice. You were just kind of exploring to see which language would work best.
Yeah, I wanted to see. Yeah, I was sort of interested. So I started off with the NIM thing because that compiled to C, and I was trying to find like a productivity-oriented language that would just give people a different experience. And I was kind of curious to see what the performance would look like. Then I was kind of interested. So then I kind of stumbled across the code on compiler and I was like, oh, wow, there's like a native code compiler for Python. That's crazy. And so that was just another, and it supports OpenMP. That's kind of interesting. So why not see what happens when we drop, how difficult would it be to go through this exercise? And between the two, the code on tool suite was a lot easier to deal with.
Having gone through it, then what would you recommend? If I were to start a new project, I wanted to make use of OpenSHMEM. I wanted it to be really easy to write.
I would probably go down the code on route personally. There were less gymnastics I had to go through to get that code working as compared to the NIM code. The NIM code required that macro I think I showed earlier. Let's see if I can find it. Yeah, it requires this to do the magic. So if you don't drop that in there, you'll get compilation errors. And I'm not a big fan of having to force users to do that sort of thing, right? So on the other hand, I think if I was a new user and I was interested in doing something, this seems a little bit more like, simplistic. So
There have been kind of couple of efforts in OpenSHMEM to create bindings, right?
yeah.
Like we had like Z coming up, and you also have Python-like space, coarrays and all other stuff that has very similar semantics, right? It's like bottom line translate to array assignment. I'm wondering like how is there any discussions with OpenSHMEM community to drive some sort of alignment on this? I remember like we had post-thread supercomputing probably. I want to say 7 years ago without OpenSHMEM Python bindings.
Yeah.
I don't know if I think it actually was Aaron. He was online earlier. So like it has been, you know, going on and off, but bottom line, nothing really came out of the community.
Yeah.
I'm wondering like if there is no traction or.
I wouldn't say it's from a lack of interest, but I don't know. I would think, given the popularity of that language, it would be a pretty easy sales pitch. Then again, is there a lot of application code out there that people can look at as an example to sort of figure out exactly what to do with something like that? I think that might be part of it.
Some of this is fashion, right? There's Rust.
Yeah.
You know, this language is coming up.
So, yeah, that about sums it up. Again, my apologies for being so quick and blowing through the slides here. Want to thank everyone at ARM for hosting us this week. It's fantastic. And again, if you have any questions, you can contact me, ctaylor@tactcomplabs.com. And I'll see about getting that other chunk of code up on the net on GitHub. So my Git repository is ct-clmsn. So with that, oh wait, we got a question, I guess. There's a Go binding. It's older. Someone's looking at it now. Oh, it's Steve's looking at it. That's cool. So that kind of gets to your question about coming up with other interfaces for OpenSHMEM. It'd be nice to see more of that happening, or get maybe a revival, if you will, on that kind of work. And Aaron has the old PySHMEM stuff. That's cool. All right. Who's next?
Good. Okay, so welcome. Yeah, I'm Savatore, and today I'll be discussing a bit about offloading tag matching logic to the data path accelerator, or DPA. So basically, the motivation a bit behind this work is that if we look at like the evolution of communication and data transfer speeds, we see that there are significant improvements at each generation. So last generation we were at 200G, next generation we are going to be at 800G. So this trend kind of suggests that optimizing communication overheads like MPI tag matching becomes more and more important. On another side of the story, there is another trend, which is GPU-centric communications, and where basically the GPU is the one initiating or triggering the communication that then happens through the NIC. So I stole this slide from Jim's presentation at the XMPI keynote, where the question is basically, is MPI missing out in the context of GPU-centric communications? So the idea is that like there are few components of MPI, and speaking about the two-sided semantic, so send and receives, like that prevents like a full adoption of MPI for this GPU-centric vision, right? And one of these components is exactly MPI tag matching and the handling of unexpected matching, of unexpected messages, sorry, which kind of forces like the presence of a proxy process on the CPU, which is on the data path, right? Because you receive a message, then you need to match it, and then you can actually signal the GPU that the message arrived. So the question is, can we offload MPI tag matching to smart NICs? And this will kind of, on one side, offer a full offloaded solution for both tag matching and for the handling of unexpected messages. And on the other side, it will remove the CPU from the data path. So in the case of the GPU-centric communication vision, right? So, but before going a bit more into details, let's quickly recap what we mean by tag matching. So this is this belongs to MPI semantic for point-to-point. So this means that basically in this example, we have two ranks, rank 0 and rank 1. Rank 1 can post a bunch of receives. In this case, it's non-blocking receives. It doesn't really matter. And you see that each receive has a tag and a source, right? So then we can also have wildcards, so any tag or any source, meaning that this receive can accept any message, can accept messages with any tag, and similarly for any source can accept messages from any source, right? So on the other side, on the sender side, we have the sender that specifies explicitly the tag and the destination, so no wildcards on the sender side. And then once we get messages on the receiver side, we need to understand to which receive we have to match it, but meaning that to which receive buffer we have to actually copy the incoming data, right? So, and now it's not so easy because then MPI also specifies some constraints on the ordering with which these receives have to be matched, and we will quickly recap them later. So, and an additional thing is that if a message arrives when the receive is still not, when a matching receive is still not posted, then this message is unexpected. And this basically also means that we need to do two-sided matching. So we need to do a matching when we get a message, and we need to find a matching receive. But also we need to do a matching when we post a receive, and then we have to match against an unexpected message. At least try to match, right? If we match, then the receive is already completed. Otherwise, we can post it and wait for new messages to come. Okay, so the question is, where do we offload it, right? So, of course, we consider the NVIDIA Bluefield 3 DPU as our target SmartNIC, which has two programmable units, so as the 16 ARM-A78 cores in the ARM subsystem, and the data path accelerator, which has also 16 cores, but those are RISC-V, are lightweight, and 256 thread contexts. So now if we look a bit in more details on the architecture of the DPU, we see that we get data from the network, and then we have the NIC subsystem. So where that implements transport and where the DPA basically sits. And at this point from the DPA, from the NIC subsystem, the data then can flow either towards ARM memory or host memory or GPU memory, right? So in this work, we try to understand if MPI tag matching can be offloaded to the DPA, simply because DPA is optimized for IO-intensive workloads, so it looks like a good place where to have tag matching. So before getting there, so how do we actually do that? Let me quickly introduce the DPA subsystem. So basically, DPA is an event-based architecture. The idea is that on the application side, you define some event handlers that you write in C. So this is application code. It's not like higher privileged code. And then you specify some events to which you want to bind these event handlers. So you want to say, okay, whenever these events happens, I want to trigger this event handler on the DPA, on one of those RISC-V cores, right? And then basically the application can utilize the Docker libraries, either Docker DPA to have a higher level abstraction, or directly FlexIO for a lower level abstraction, in order to implement kind of the control plane of handling, of managing DPA processes, event handlers, and so on, and can invoke also directly DPA event handlers through RPC calls. So it can issue RPC calls, trigger the event handler or the DPA function, and then get back a result. The other way, which is actually the one we use in this work, is by associating the event handler with a completion queue. So basically we say whenever there is an event generated by a completion queue, so whenever we get a cookie and the CQ is in an ARM state, we want this event handler to run, right? So on the DPA then, the event handlers, so the application provides, can use the device side libraries for Docker DPA or FlexIO again, in order to communicate with the rest of the world, like to use DMA engines or NIC doorbells, memory windows that I'll describe in a second, and so on. On top of that, there is a DPA real-time operating system that also kind of enforces process isolations and provides services. So if we look a bit more into the DPA architecture, we see that we have 16 total cores, and each core are 16 threads. Each thread has its own L1 data, and they share the L1 code. At that point, then we have all cores basically share L2 and L3. And we also have the concept of memory windows that basically allow to map some external memory to within the DPA process addressing space. So basically, we can access, for example, host memory or GPU memory via load and stores directly from the DPA. It also has fast access to the doorbell interface on the NIC and interrupts. Right. The model is run to completion. So when you get your thread running, you can run it to completion, and kind of you then need to give up the core in a cooperative way whenever like you find that you don't have any more work to do. We will see an example of how like FlexIO code works, but before that, like the full picture on the software stack is that we have applications, again, the Docker DPA library that provides some higher level abstraction, and then the FlexIO library. Good. So now, how do we actually run stuff on the DPA? So the idea is that the user writes the event handlers or kernels directly in C code, and then compiles them through DPA-CC. So that also takes as input the Docker DPA device side library. So this is code that runs on the device, so compiled for the specific architecture. And then it gives you a DPA program that you can link together with your host application side, and also takes a Docker DPA host side library, so a typo here. And this all produces a host executable where you can call FlexIO or Docker DPA functions in order to have RPCs or install event handlers that get triggered according to network events. Right. So an example, like a toy example of a FlexIO event handler is the following. So you can define your function. This is the function that will run on the DPA. So you decorate it with DPA global to mark it as a function that can be triggered, let's say. And this takes an argument. And in this example, what we do is just get the completion queue associated with this handler, like to understand what event actually triggered us. Imagine you want to read the cookie. You do some work, and then once you finish, you arm again the C queue in order to be again triggered when the next cookie comes. And the idea is that here you can also do some polling, right? So you can get triggered, then maybe just serve more than one one cookie, and then finally, when you are done, you release the thread. On the host side, instead, what you want to do is to create the FlexIO process. So this is an entity for the DPA. Then you create the event handler. So you can imagine this as a thread. So here you say, okay, this is a thread of this process, takes this function, right? And these arguments here that then go here, and you get an handle back. And here we show that you can create your CQ and then associate that CQ with a specific event handler. This is the handle you got back from the handler creation, right? So at that point, basically every time the CQ is armed and you get a cookie, you will get this function executed on the DPA. And finally, you signal that to the system that you are now ready to run. So you kind of enable your event handler to be scheduled whenever the triggered condition is satisfied. Okay, so this kind of finishes the brief intro to DPA. So now let's see how we want to use this for tag matching. So let's go back to the main topic. So the high level picture we want to achieve is something like this. So we get MPI messages from the network. Those are served by the DPA. In particular, just look at the headers. We don't care about the data, where the tag matching and the handling of unexpected messages is run. And at that point, the data can be steered through the ARM memory or CPU memory or GPU memory, right? So now, now that we have seen a bit about the architecture of the DPA, we see that those are lightweight RISC-V cores, right? So kind of the idea to extract performance, you want to extract parallelism. So the question here from can we offload MPI tag matching to the DPA becomes more, can we extract parallelism from the MPI tag matching, right? So to do that, what we have is we will go to parallelism in 1 second, but before this is what the data structures and the components, the software components we keep on DPA. So we have the NIC, DPA, and host. So on the DPA, we want to execute 2 software components or stages, right? The matching itself. So given a message, we want to understand which receive this message matches to. And then once we have this information, we want to execute the protocol. And now this can be either eager or rendezvous or just handling an unexpected message if we didn't find a receive, right? So we also keep data structures here to index the receives, to have like a list of shadow buffers where to copy messages if a matching receive has not been found. And finally, we keep an index to remember where the unexpected messages are. Like we get a message, we put it in a shadow buffer. We need to keep an association between that message and that buffer. So we can do this two-sided matching we said before, right? Remember, even when you post a receive, you still have to do some matching. And this is the index, let's say, that then you want to check. Okay, so you get the data. The matching phase searches the receive index. In this case, is CC, this is expected and eager. So we find actually a receive. And then we pass the ball to protocol, right? Which will implement, in this case, eager, that basically consists in copying the data to the receive buffer. And the receive buffer was specified here, right, in this receive. So this is like really high level. Now, what we will see next is a bit how we actually implement these indexes, like the real data structures that are behind those, and how we implement the matching phase. So we were discussing initially that MPI has imposes some constraints on the receive ordering, right? So in particular, there are 2 constraints which we need to take care of. The first constraint says that if there are 2 receives matching the same message, then the oldest one has to be matched first. Like here we have receive 0, receive 1. They both match this message here that is coming from the network. Now receive 0 means that this receive arrived first. We need to make sure that receive 0 actually matches message 0 and not receive 1, right? The second constraint is kind of the other way around. So if we have 2 messages coming from the same sender and they match the same receive, well, then the oldest message has to be matched first. Like again, we have message 0 and message 1. They both match this receive 0. We need to make sure that message 0 actually matches receive 0 and not message 1. Right. So now let's see how we kind of take care of these 2 constraints. Well, constraint 1 is let's say taken care of via the way we index receives. So we use an hash table approach, and basically we classify receives according to which kind of wildcards they have. So we can have 4 possible combinations: no wildcards at all, only source wildcards, so any source, any tag, or both any source and any tag. Right. Another observation is that if we just consider one index now, let's just focus on one index. If we get a receive, if we get a message, sorry, and then here there are 2 receives that can match the same message, well, we can satisfy constraint 1 if we make sure to match those in order. So once there is kind of a conflict here, the conflicting receives have to be scanned in order. Right, so we need to first try to match this receive that arrives first. We always append at the end of a bucket, right? When new receives come, and then we try to match the second one, right? So this kind of satisfies receive 1, constraint 1. But now the problem is that we have multiple independent indices, right? So what can happen? Basically, the matching process says, okay, let's try. I get this message. I will check in this index, in this index, in this index, and in this index. So now this means that basically you could have multiple receive candidates. that match that message, right? But only one has to win. And the one that has to win is the one with the lowest sequence number. Sequence number is just a counter that we increment every time a receive is posted, right? So in this way, we kind of select globally the oldest receive that match that message, right? And this allows us to satisfy constraint 1. Now let's move to constraint 2, and let's also take into account what we said before, that we actually want parallelism, right? So this is the scenario is that we get a stream of messages, like message 0 comes first, then message 1, message 2, and message 3, and so on. And what we want to do is have different DPA threads, so different DPA event handlers, taking care or processing different messages at the same time, still enforcing those two constraints, right, that allow us to implement the MPI semantic. Okay, so the way we do this is we call it optimistic match. And the idea is that, okay, each thread will just try to optimistically match against the received indices, right? Without any lock, without any synchronization, nothing, just try to match. Okay, so now what can happen, like I'm focusing here on just one index for simplicity, but we have all the others. Each receive is basically other than the classic informations, like, okay, the receive buffer, the matching information. We also keep a booking bitmap. Right? So this just says, okay, this is for the first bit is for thread 0, then for thread 1, and so on. So one thread will flip a bit, its bit in the booking bitmap of a receive, only if it wants to match that receive. So only if it has a message that matches that specific receive, right? So just to once again, like this thread will execute this matching process. So like try to match independently against all these indices, come up with a receive candidate, selecting the minimum here if there are multiple candidates, and then we'll go and mark that receive as booked. Okay. At that point, we need to make sure that everybody actually finishes. So we have what we call partial barrier. Partial barrier is just that we don't have to wait for everybody, but like thread 1 waits for thread 0, thread 2 waits for thread 1 or thread 0. So each thread just waits for the threads behind them, right? This is simply because remember that constraint 2 just says that if, for example, message 1 and message 0 match the same receive, then message 0 has to win. So we don't care about the messages that come after us. We just care about the messages that come before us, right? So, and also like this wouldn't work with the global barrier because maybe message 3 will never arrive, so you will get stuck with the other threads. Okay, so once we have this partial barrier, we know like that all threads mark, or at least we know that in the interesting threads, the threads that are of interest for us, match the receives, and we can check for conflicts. So in this case, now we see that thread 1 and thread 2, they all want this receive specifically, right? And we already know that thread 1 is going to win because that's what constraint 2 tells us, right? The message that comes first has to be matched first. Okay, so thread 1 we just say, okay, look, fine, I won, I can move on, and thread 2 now has to do something, right? In particular, now there is a bit of a catch because now we need a global indication of conflict. So I'll explain in a second why that's needed, but basically this means that we need another partial barrier here, and just to understand when everybody marked its status, like conflicted or not. After this phase, there is the conflict resolution phase. So this happens only if there is a conflict, right? So for thread 0 and thread 1, this doesn't happen. It has to happen though also for thread 3, even if we saw that thread 3 didn't have a conflict. But now the problem is that thread 2 wanted a receive that has been taken by thread 1, and now has to redo the matching basically. And suddenly it could take the receive that thread 3 wants. So now we have to kind of redo the matching and enforce synchronization here to make sure that thread 3 matches or checks if its receive has been taken by the previous threads, basically. After we do this phase, we can actually finally implement protocol, That means eager, rendezvous, or unexpected messages. And of course, like we realize that a message is unexpected already in this phase, right? Because if we don't find a receive in this phase, then we will not find a receive later when other threads will try to match the receives that are currently indexed. Good. I mean, if there are questions at any time, then feel free to interrupt me. And okay, at this point, the thing I want to address is how do we handle unexpected messages? One thing which is important is that conflicts are time dependent. So this means that we have conflicts only if we get a stream of messages and we actually get concurrency in processing those. Like in this case, if message 2 comes a little bit later than message 1, well, then when thread 2 tries to match it, it will already not find that receive that has been taken by thread 1. So like it's not like if there is a conflict, you will always experience it. It's also like a time-dependent factor. Okay, so now how do we handle unexpected messages? Well, the idea is to use this thing that we said before, that we do matching also when we have a new receive that is being posted. And what we want to do is to index unexpected messages in a way which is similar to the way we index receives, right? So now, what basically this means that we have, again, 4 indices, no wildcards, any source, any tag, and both any source and any tag. And then we index the unexpected message in each one of those indices, right? So these are just pointers, they don't take a lot of space. But basically, this means that we need to have the hash of source and tag and put it here, hash of only the tag and put it here. This is because then when the receive comes, it could fall in one of those indices. But once we have this kind of indexing, the matching like that happens when a receive comes is very similar to the matching that happens when a message comes. Now here we have receives, so now we are seeing receives that are being posted by the host and not messages, right? So we still observe them in order, and we can have basically the same structure. We can just say, okay, everybody tries to optimistically match an unexpected message now, right? Then if there is a conflict, the first receive has to win, the oldest receive has to win. So this means we need to mark the receive as we did for, sorry, we need to mark the unexpected messages as we did before for the receives, resolve the conflict, and then run protocol. Because again, if we match, then we need to run either eager or rendezvous. And again, if during the optimistic matching we don't find an unexpected message that matches this receive, well, then fine. We can just skip all this and just go to the receive insertion phase, the receive indexing phase, right? Okay, so now probably at this point you have realized that there are like 2 ways, performance-wise, there are 2 ways of operating of this approach, right? There is a worst case. The worst case is where we have always conflicts. So basically all threads, all messages will always match to the same receive, and they all arrive together, right? So the question we asked is, okay, how frequent is this, right? How frequent is this scenario? And what we are doing is a bit of static analysis of application traces and trying to understand how frequent are these conflicts, right? So in this plot, you see the number of collisions a receive would experience, and on the x-axis you have the runtime of the application. And each subplot is basically for a different index. Like remember these indices that we have here. So no wildcards is this no wildcard here. So if a message comes and matches a receive without wildcards, okay, how many conflicts did we have there, right? How long is this bucket basically? And then we do this for different bucket sizes. So like how many hash table entries we have in each index. So with 16, we have about 10 here, but then we can see that as we approach 128, 256 buckets, actually they go close to 0, right? And there are other cases where we have this spike. Like this means that at this point, the application just posted like about 20 receives that were exactly the same, like same source and same type. In this case, any source, and they were using the same type. And one thing I didn't say here is that this is a trace with more than 1,000 MPI ranks. And what we do is basically to aggregate all this data, we take the maximum. So at each receive, we take, okay, this is the maximum number of collisions that any rank experienced at this point in time. Good. And we do this also for other applications, and we kind of notice the same, a similar behavior that like using 128 to 156, we are able to not have conflicts, right? But this is still possible. So we also thinking about optimizations for that specific case, and I will quickly describe one we are thinking of. But just to show you some performance numbers, so this is by classical OSU bandwidth benchmark. So sender, receiver, we send a bunch of pings. So these are small messages, and get a pong back. We do this 500 times, and every time we have 100 pings. And what we show here is the message rate as function of the DPA threads. So how many DPA threads here we are using. And we can see that basically using 16 threads in the non-conflict case, so where we don't experience conflict, we reach about 7 million messages per second. And kind of the message rate is like not the only, but is the metric of interest for us, because basically these DPA threads do not care about data, right? So whatever the message size is, their job is just to do the matching, which is independent from the data. They just care about the header, right? So the idea, I mean, for this preliminary result is to see, okay, if we can get to the message rate for small messages, then we should be able to get for the message rate also for larger messages, and then we will be bound by whatever other bottleneck in the system. Where by system I mean the NIC DMA, the PCIe, or the memory bandwidth, right? So this kind of gives us an indication of how good is this parallelization, right? For the other case, this case is really the worst case for us, like all conflicts. So basically, we get all receives that are matching to the exact same, sorry, we get all the messages that are matching to the exact same receive. And all at the same time, basically back to back. But if we think about it, there is also a way to optimize this case. We still don't do this, but we are still like thinking. And one way would be, okay, we have this index here. If we see, one slide, if we see that actually we have a sequence of consecutive receives that are exactly the same, and all these threads wants to match the same receive, well, then they just map naturally, right? Because if we know, okay, we have 4 receives, for example, that are exactly the same, they just change in the receive buffer, right? Then we can just say, okay, thread 0 will map the first instance, let's say, of this receive, thread 1 will get the second instance, and so on, right? So in this way, we could actually save this additional synchronization that we have here, and that kind of slows us down in the worst case scenario. So so again, this kind of concludes the talk. And just to recap, we motivate a bit the need of having offloaded MPI matching and handling of unexpected messages. And we do this on the data path accelerator, and propose a way of dealing with tag matching that is kind of optimistic. So it tries to match and then eventually resolve conflicts, and presented some initial preliminary results. So that would be it. Happy to take questions.
I have many questions.
I knew it.
First question is, if I understand correctly, you're not using the hardware tag matching offload at all, right? It's only code running on DPA eventually.
Correct. Yes.
second question is, how do you make the received data to be placed in the right place in the user buffer? I assume it's not going through the data path in DPA, right? After
right. So currently what we do is just issue an RDMA write with immediate from wherever we stage the data, and this could be another question, to the receive buffer, right? And the immediate serves to notify the host that the receive completed, basically.
So it's staged in DPA memory, and then you do RDMA to copy from DPA memory back to the host, right?
Correct, correct. And yeah, we also try to stage in host memory because, I mean, we just have more memory there to scale better. The problem is then that we kind of overutilize the PCIe because now we have data coming from the NIC to host memory, and then we again moving data from the staging memory to the host memory. So one thing we are looking at is staging in DPU memory. So so the ARM DDR basically. So we stage there and then have the RDMA write from the ARM DDR to the receive memory, to the receive buffer.
Did you see any issue that of utilizing RDMA engines, if you have, for example, bidirectional traffic, that because you use RDMA engines both for network operations and also for copying between between DPA memory and host memory, there could be some bottleneck there. We saw it.
You mean? Okay, you mean for when using the DMA engine on the NIC?
Yes.
Right. Yeah, this is something we still don't check. We run some scalability tests with multiple PPNs, and we see a degradation at some point. So this could also be a reason.
And another question: there was a slide about unexpected messages, and in that slide it was written something about wildcards in unexpected messages. So what does it mean exactly? Because when messages arrive, they always have specific source and tag. So
you mean here, right?
Yes.
Correct. Yes. The problem is that then when the receive comes, you want to match again those independently, right? So the receive then, when the receive gets posted, that can have wildcards. Right, so it's to kind of better distribute, to lower, let's say, the probability of conflicts, right? Because now, then the receive can just go to exactly the bucket it needs to check.
So would it be correct to say that a big part of the solution you did is actually implement a multi-threaded tag matching, which is not necessarily for DPA? But it could be used for host code, which multi-threaded matching.
Yes, absolutely. That's the correct way to see it.
Yeah, that's really awesome. Anybody else have a question?
Yeah, I have some questions.
So I guess the first question is, how does the DPA version compares to hardware tag matching in terms of performance?
So I don't have the data right here, but at least in terms of message rate, and Yossi can correct me if I'm wrong, I think hardware tag matching kind of compares to software tag matching, like they are in the same ballpark.
Right. That's with how many DPA threads?
We're using 16 right now to get
16.
to 7. Right.
Okay. Another question is, because this looks like around 7 million message rate. So I was wondering, is this like how many processes are communicating, or is, how does this DPA tag matching scales when we have like multi-threaded MPI communications?
Good point. Good point. So basically, we have 16 cores, and each core has 16 threads. But of course, if you fully utilize everything, then you are going to see some drops, right? So So basically what we observe is that up to between 4 and 6 processes per nodes communicating at the same time, we have good, almost linear scalability. Because the nice thing is that while here we are kind of impaired by scalability in number of threads because of this synchronization, if you just deploy multiple of these, they are completely independent, right? They are completely independent sets. So between 4 and 6, we scale until between 4 and 6, we scale nicely. Then we start seeing a drop because DPI resources are not enough for this context. Again, I think this is kind of a borderline use case for DPA, if you ask me, because DPA is good for like I/O tasks, but this involves some synchronization, right? That kind of makes things a bit more heavy, right? But as we were saying in the beginning, like if we look at HPC use cases, especially, or GPU-centric use cases, then we don't see a lot of processes per nodes being deployed, right? So, yeah.
Right, because I was thinking at so if you go back to the matching, essentially having 4 threads, matching thread that have partial barrier to synchronize them. Essentially, it's like a 4-stage pipeline, right? So ideally you have one barrier and everything matches, and worst case you have 4 barrier, maybe 3 barrier, 4 barriers. Basically, I have to match 4 times to resolve the conflicts. So I was wondering, because if the upper level can identify that some of the messages are coming from different processes or essentially from different contexts, then theoretically you can kind of separate them, because you know there's no ordering requirement between these 2 groups of messages, and then you can have maybe instead of 4 threads matching on the same stream of message, maybe you can have two group of each of have 2 threads and matching on different part of this message stream.
Yeah. I mean, if I understand correctly, your point is if we realize, for example, that message 1 and message 0 come from different senders, then we don't care, right? About their relative ordering. The problem there is that then this thread has to get the knowledge from this message. Right, that is a different sender, and so this kind of introduces then a serialization here in this part at the beginning, because now while each thread kind of jumps by the number of threads, so thread 0, then we look at message 4. Now all threads have to look at all messages, even if like for some messages it will be very quick because they just have to check the sender. Still, they have to go through them, right? And this means additional cache misses and so on.
Right. So,
but in principle, I agree.
Yeah. The reason I'm thinking because this is a software-defined technology essentially, right? So in addition to source and text, you can have additional fields to identify whether it's these message or these receive are for the same stream of message, or they're actually independent streams of message. In that case, you'll be able to identify.
Right. For example, correct. For example, one thing that I completely ignored for simplicity in the talk is the communicator, right? So NPI communicators, the matching between communicators is independent. So communicator will be one example of this. Right. I agree.
Okay. Cool. Yes. Thanks.
Thanks.
Did you happen to look at the latency with that solution compared to, let's say, a native send receive or harder tech matching?
Right. Yeah. I mean, this is a software solution and is kind of a bump in the wire, so we expect it to add latency. So we run some simple analysis here, and so basically this is a relative latency overhead. So like for small messages, we kind of take 70% hit on the latency, and this gets down, of course, with the message rate, because then what counts is
how much is it in absolute numbers, roughly?
So basically, the overhead we introduce is about 1 microsecond, while I've seen from the UCX profiling when running software tag matching, it spans between, I think, 300 and 400 nanoseconds for small messages there. So yeah, because I mean, if you consider the single message latency, there we go through all this, right? So let's say that this approach is more optimized for sure message rate and latency.
I'm just thinking out loud if it's not really tag matching, but maybe we can look at the other requirements we had with signal or some kind of queue. If we could implement it by running code on DPA, something like collecting, like do input with signal from DPA, because there the latency is not so important, but we have the same approach when you receive a bunch of messages and need to do some kind of logic to understand what is the right place to put them and then signal the host. So, yeah. Okay,
so basically these are put, which are, you still need to understand, okay, I see. So it's a simplified matching, basically.
Yes. Yes.
Yeah.
Also, did you consider things like out of order or adaptive routing or multiple?
Well, this is the nice thing about this approach, right? That kind of solves this because this runs above transport, and transport is supposed to then always deliver in order.
Mm-hmm.
Right.
Okay. Any more questions?
Thank you, and very interesting talk. And my question is, what is the programmer effort while doing this? Like, I imagine like writing the DPA kernel, maybe modifying stuff, right?
So, I mean, writing the code is not so hard. Then tuning them for performance is a bit more challenging in my experience. But I know that there are new tools coming up, software tools that can for sure help in profiling and debugging, so to make life easier.
Thanks.
You're welcome.
Any other questions?
Okay, hello everyone, can you hear me, hopefully, and see my slides?
Mic on, we're recording, we're good to go.
All right, so I'm gonna talk a bit about our latest developments during the last year of the UCX core team and other teams at NVIDIA, and also would like to have some discussion about plans for the next year, hopefully to hear some inputs or other approaches that people can see regarding our task for the next year. So one of the main changes we did is enable protocols v2 by default. As part of that, we did extensive performance tuning, mostly by Mikhail's team, Ivan and Raul on the call. So these complete people who know, who are aware, the protocols v2 is a complete change of how we select transports and devices, and how we implement the logic of sending messages in UCP on top of a UCT layer. Part of that, the main focus was to improve GPU memory handling, including locality detection. So instead of all the logic that we had in one place in rendezvous.c that had a lot of branches and ifs and checking various corner cases, which is not scalable in terms of code design. We separated each logic to a different protocol, each in its own file. We have separation between, let's say, pipeline protocols and zero-copy protocols and active message-based protocols. Each has its own logic for performance estimation and logic for sending messages. The logic for performance estimation is the key part which decides what is going to happen at runtime. The more accurate the performance estimation is, the more it's closer to the actual performance of the protocol in a real scenario, the better threshold and cutoff and the smoother graph we have for all the performance data. So instead of trying to find the right cutoff between every possible pair of protocols, which is again not very scalable, because many things have to be considered. Each protocol has to be able to estimate its own performance in the best possible way. And then the common logic, which is able to take all protocols and select the best one for every certain message range. As part of that, there is also unified logic for sending, packing data, and packing data. We introduced a data type iterator data structure, which replaces a code of any data types in multiple places. And we use this code also in a lot of common inline functions that are sending protocol data. Then we were able to finally add support for GPU memory for RMA and atomic operations, which was incomplete and not really supported in protocols v1. We also were able to reduce software overheads for request initialization. We need to use less fields in UCP request. We can unite things between send and receive. And eventually we would be able to reduce the size of the structure. And also because we have less branches in the fast path of selecting and checking things, the overhead of rendezvous protocol is lower. We can see better performance of rendezvous protocol for smaller messages, let's say 4 or 8 kilobytes. As part of making it default, we run extensive performance testing on both host memory and GPU memory on internal clusters like Selene and other clusters in the lab to make sure we don't have any degradations compared to Proto V1. We were able to solve most of the differences. It was mostly related to tuning the performance estimation, tuning constants like shared memory, estimated performance, GDR copy estimated performance, and so on. There are still some gaps where we see that protocol v1 was better, and we plan to address them in the next release. In the next year, we plan to continue improving protocols v2, both in terms of performance and features. For the next big thing is the device memory pipeline. We had discussion about it with Akshay in the first day. The plan is to have protocol variants. So each protocol could instantiate itself multiple times with different parameters. So specifically the rendezvous pipeline protocol could create several instances of itself with different candidates for buffers. And then the common logic that selects the best performance protocol would compare the estimated performance with device memory versus GPU memory, and would be able to select the best one. It could even mix and match. So for a certain range, it would be device memory, and for other range, it would be host memory. And of course, it would be able to select the device on which the buffers would be. So it would be on the GPU that is closest to the memory that is provided by the user. We also plan to improve our performance estimation. During our tuning work, we identified the gap that when we have protocol like rendezvous, we assume that we always take the estimated performance of the remote side, and on top of that, we add the estimated performance of our side, but it's not always the right thing to do, because in some cases, the performance of the remote side also has some cost, for example, on the local CPU of our local side, if it sends some messages to us that we have to process. So we plan to introduce some data structure or some common logic that can take into account the CPU utilization of both sides across a rendezvous protocol. So hopefully it would provide a more accurate estimation. And we plan to do a performance tuning for Grace Hopper platform. Part of that is going to be introducing some sort of database or a configuration tree or YAML or some hierarchical structure that would capture a performance characteristic of a specific system. For example, posting a doorbell on x86 is not the same as posting a doorbell on ARM CPU. Maybe PCI latency is different. PCI latency actually can also be different on different x86 systems, depending on the server type, the amount of switches, and so on. So we plan to introduce something that would be able to provide a more accurate information than what we have today. And if the specific system is not there, we would continue using the defaults that we have today. In addition to protocols v2 and all the things that we discussed and we're in the past few days, we are working on additional projects not mentioned in this slide. We're doing something called the RDMO offload. It means that a client, actually initiator, is going to send a RDMA write, an atomic operation, to a DPU on the target side. And instead of waiting for the fetched atomic value before sending the RDMA write, in order to know the remote address that it can write to, everything would happen on the remote DPU. So there would be a single operation, single active message sent from the initiator to the target DPU. That message would contain the address of atomic variable and maybe the base address that we want to write data to. The DPU would be able to execute an atomic operation on the target side. And after the atomic operation is done, it would write the data into the calculated offset. That would avoid the need to progress things on the sender side and also reduce the network round trip time on the sender side before posting the RDMA write operation. Currently, we have a working prototype, and it's in performance tuning stage. The goal is to get a full wire speed to reach the network capacity with all-to-all benchmark. We also continued working on a Nickel UCX plugin. So it was work started in a Josh team by Sergey Lebedev a few years ago. And due to some gaps found in UCX, the work was paused for a while. And since then, we added many features in UCX, so we were able to continue and resume this work. In recent months, we were able to get a substantial performance improvement. The sources for performance improvement are mainly using separate worker per thread and implementing a Nickel multi-receive plugin API. Prior to that, the multi-receive was like doing one receive at a time, which is not very efficient. In addition, we identified some stability and deadlock issues that are related to using CUDA calls from the plugin, which interfered with Nickel kernels. So currently, the Nickel UCX plugin avoids any type of CUDA calls, and everything is done by GPU direct only. I guess it has something in common with what Hesam needed for Legion to force a zero copy path, but for another reason. Another thing we're looking at is on-demand paging, ODP. It means that the hardware is capable of sending page faults from the NIC to the CPU. Instead of using a registration cache and making sure things are pinned before doing the operation, we can let the operating system move pages. And if something is not found during the communication phase, the driver, with the help of the software, would populate the pages. So we can see one thing we can do with it is to implement a hierarchical structure that resembles the page table of the CPU and use a single memory key that would be hierarchical and cover the full address space of the process instead of using, let's say, different key for every segment. It would allow, for example, to bypass several functions calls on the data path, and also when Artem presented the symmetric key feature earlier today, we still need to have a key for every segment. Now, even though it's not a key per remote peer anymore, but it's still a key per segment. But with this feature, we can have a single key for the whole process. Except working on the core UCX library, we also maintain several other projects in the UCX community that we had a chance to optimize during this year. We took ownership of XPMM driver in the sense that we forked it, and now we fix bugs in it, adapt it to new kernels when needed, and do some optimization. So in last year, we had a pretty substantial optimization work in XPMM related to pinning pages. So what used to be is that XPMM, whenever it got a page fault happens when, for example, you would try to access a mapped page, but it's the first time that it's being used. So it used to pin the page, do all kinds of lookups, translations, checks, but it's not very efficient because it's done on every 4 kilobyte page. So if you have to copy a relatively large buffer between processes, and that buffer was just allocated by the application, that it's not very efficient. We saw that, for example, when using a CMA kernel transport and running a LeanPack application, there was a better performance than running XPMM. So in order to solve this issue, we added a prefetch into XPMM backward and forward. The default is 32 pages. So assuming that if we access some page, we're most likely going to access the page, the nearby pages as well. And the cost of additional pinning is not very expensive. We could use different kernel APIs that operate on memory ranges instead of doing it only a single page at a time. And eventually, we're able to reach the same bandwidth that CMA does. Another thing done in architecture team is to improve a SHMEM log scheme in OpenMPI. It uses a MCS scheme, which is now enabled by default, and is more efficient on a large scale. Any questions? Okay. So for next year, we plan to have extensions for active messages. The most important one is going to be a fetch API. It means that instead of pushing data from the initiator to the target, we're going to send some small header, and then the target would be able to send data back to the initiator. There are a few motivations for doing this. For example, for storage applications, when we want to read some data, we would have less round trips this way. No need to have another synchronization. Also, when working on a Spark DPU project, we identified a performance issue that when the initiator tries to read data from the target as part of a fetch blocks operation, we don't want to have any additional progress on the initiator. We just want to send the request to read blocks, and then we want to have the blocks ready in our receive buffer at some point in time without progress in the network anymore. So in the current API, we need to do an active message to from the target back to the initiator, which requires the initiator to receive a callback, to post a receive, and then wait for it. But instead, we could use the RDMA write. So the target would just write the data back to the initiator when after the data is read from the disk. And the API to have it is going to be active message fetch. So also, it's something we identified a while ago. Currently, the way that active messages are defined, all the receive have to be placed in a single buffer. So if we receive the message by multiple fragments, it's not efficient to allocate and copy them to a single buffer. So we want to define an API that will allow the user to receive each fragment separately, potentially out of order, and so each fragment would be received with its offset, and the out of order networks could take advantage of that. So as we spoke with, as Hessam pointed out in the first day, we'd like to have a priority per operation. It means that whenever we call UCX API that sends something, we would have an optional parameter to specify high or low priority. We're still figuring out if we want just a small set of priorities or allow the user to query or specify the number of priorities to have. The complicated part is going to be on the transport layer, because we would need to open different queue pairs for every priority, and the transport layer would have to schedule the message accordingly. Also, it would mean that we are changing the ordering semantics, because if we try to maintain ordering, it would mean that priority is not really taking place. So we have to define that different priorities would be out of order with respect to each other. We're going to continue working on a Nickel UCX plugin, continue performance tuning for different use cases, message sizes, and benchmarks. This year, we plan to tape out ConnectX-8, and it's going to have a very nice feature of improved receive queue. It means that we could post a relatively large receive buffer, let's say 32 kilobytes, and if smaller messages arrive, they would not consume the entire receive buffer, but only a part of it. But on the other hand, if a large message arrives, it would not be split between different receive buffers. So we would not have to copy or assemble any fragments. This way we can improve the memory utilization on the receive side, improve the cost of unexpected messages, and also improve the message rate, because smaller buffers would have to be consumed, it has better cache locality, and so on. Okay, so actually this is it. Any questions or comments or anything else you would like to see next year in UCX?
Yossi, I have some questions. First, with what you mentioned with regards to plans, you mentioned there's rendezvous protocols with use of other buffers than hosts that's going to be introduced. For that, do you see that there's a way for users to override functions? Because one of the things you mentioned was Proto V2 was going to select buffer types for different message ranges potentially, right? Based on the estimates that it gets. But there may be cases where users want to enforce that. But generally speaking, in protocols V2, users have less of a say in how you can enforce a certain decision. Do you see some way that users can enforce, say, only using pin device buffers, for instance?
I think there was already configuration parameter that you added.
Right.
Protocol V2 is going to make a decision unless the user says something else. So the defaults of all configuration parameters is probably going to be auto or some kind of default that lets the protocols to auto select. But we're definitely going to use the configuration I think it already exists. That
Right.
says which buffer which memory types, or I think it was memory domain, that should be used for a rendezvous. Maybe we want to make it more fine-grained and also select the system device. So it would be a specific GPU.
Right. Okay. So there's some infrastructure for that, and it should be possible to do that.
Yes. Yes.
The other one more question I had was with regards to atomic memory operations with GPU memory. Is all of atomic operations currently translating to IB transport? Like, is IB the sole provider for that?
Currently, there are two options. It's either IB or active messages, which means not truly one-sided.
Okay.
So we had some thoughts about doing also atomics on CUDA copy transport, but it turned out, and please correct me if I'm wrong, that we need to write a custom kernel that would execute the atomic operation. There is no CUDA API that can do a direct atomic operation.
Correct. Like there are special instructions that don't have a driver side or runtime side API. You would have to invoke a kernel, and then you would have to issue these special operations. So that's right. Okay. The next question I had was with regards to whole VA memory key feature that you talked about. What are the main benefits there? Is it the case that we don't have to manage as many registration handles, and
Yes.
this will bring down some lookup time in the critical path, or is there more?
First of all, we wouldn't need to do a R-cache lookup. We need to probably do some kind of shortcuts because it's possible that some memory domains do support it and others don't. But potentially, we may bypass the R-cache lookup. Additional benefit is we would consume less resources on the NIC, because if we have multiple small registrations, for example, you have a large-scale all-to-all, and every message is being sent as every destination would have its own piece of the send buffer. So we would look at multiple memory registrations, unless there is some logic to merge them. But with ODP, it would just be different pages in the same memory key. So it has less overhead.
And there's expected to be no performance impact from using this whole VA memory key?
So we actually want, the first thing we're going to implement, we're going to mlock the pages that are being used. So to avoid the page migration and the unmapping, so it would be roughly the same behaviors today. I guess we'll also provide option to don't do this locking if users care more about swapping and they're willing to pay the potential performance hit of page miss.
So migration is a requirement for a platform like Gracehopper, right? So there we won't want to exercise this option.
Right. So there we wouldn't lock.
Okay. But if I understand right, you're going to make this default, and users would have to explicitly request not using whole VB and memory keys.
So we plan to do performance investigation of this feature, and then decide if it's the right thing to make a default.
Okay. One last leading question I had was with regards to extensions. So last year, Jim gave a talk about stream extensions and potentially introducing something called triggered operations, right? We had discussed this. Do you see UCP requests to be able to honor that still as we had originally thought about, given that there's it all translates to Proto V2 now? From what I see, Proto V2 is kind of independent from this because it's only estimates of what the transports are capable of doing and what to use in different stages. So do you see any blockers to that, or do you expect things to be smooth?
So from API perspective, we need to define how we set the triggers. According to the discussion we had, I think maybe a few years ago, we need to decide if we're passing opaque objects or actually passing handles to the UCP API, because UCP API has to be platform independent.
Mm-hmm.
But besides from that, I don't think Proto V2 is really important here.
Okay.
What's more important is probably how to coordinate the trigger that we're passing from the user application with the operations that we're doing, let's say, on the CUDA transport level.
Right. Okay. I just wanted to make sure that, enabling Proto V2 would not interfere with that. And it seems like that's the case. Thanks.
Also, regarding Proto V2, so at some point we're going to start removing all the protocol V1 code. Currently, they both exist in case that we have unexpected performance or functionality issues. But probably during this year, we're going to start removing Proto V1 code.
Is that deprecation going to be in line with like wire change?
It's not going to. Actually, the V1 and V2 protocols are wire compatible. Any more questions?
Not a question specifically, but I know that the list of things that you mentioned for next year is already challenging, a lot of work, I think. One thing that at least I was hoping to see was multi-GPU support
context, right?
in a single process.
Yeah, that's actually an issue that comes up quite a lot. Today, we need to set a context before doing a UCX call. Yeah, I think that's important too. But unfortunately, we don't have a good solution for it yet, but I think we need to keep discussing it.
Right. So do you think it might be something that we can have in next year?
I think that, I mean, even though we don't know the exact solution, I think that the solution itself is not going to be a lot of work.
Mm-hmm.
It's going to be constrained, I guess, on the CUDA copy or CUDA IPC transport layers. Maybe it would involve some manipulation of current context, pushing, popping things, but from the UCP protocol layer, it's already ready for multiple contexts because everything is oriented by a system device, and there's no assumption like there is a single GPU.
Yeah, I think based on our internal discussion, the challenges primarily come from realizing multi-context in the progress path. Like whenever a worker progress is called, which of the GPU resources should we be testing? Like the brute force approach is to use all, but you want to try and avoid and use only, or hence the calling thread, you should want to initialize a context or set context that only involves the specific messages that you're trying to progress.
So maybe that is not so complicated. We can progress, because even today we progress only things that we posted. We have a list of, let's say, active streams that we posted something on. We can do that regardless of the context that they were posted on.
Right. Yeah, that's a work item on our end on the GPU comms team. So I think that we will plan for that this year.
I think one issue with the progress that actually I was mentioning, if I remember correctly, was due to the fact that at progress time, we don't necessarily have a buffer from which we can somehow at least understand what GPU this progress work will be related to. But for instance, at communication submission time, we have a buffer, and at least from that we can get some information.
But I think that in progress we just look at which async operations have completed, right?
Yeah, that's true. Like at least on the CUDA transport side, you're mostly looking for events that have completed because you have already issued them.
Yeah.
So that's on CUDA transport side. On IB side,
maybe we just need to look at the. We do detect the locality every time in UCP. Maybe we just need to set the right context according to the buffer locality before making the CUDA call, not during progress, but during the CUDA copy call itself.
I mean, during CUDA copy call, we definitely have a buffer, so we can extract the context because CUDA API provides a way to extract the context associated with a given buffer.
Yes. But I think you guys already tried something like that at some point. You remember what was the challenge there?
I think we got the what is that? The paths which involve issuing CUDA API calls, like the copy engine calls, those were sorted. It's in the progress path that we didn't really fully think through if we absolutely need a buffer or not. But it seems, this is good to know that we don't actually need buffer information. We can rely on event information to make progress.
Yes. If needed, if we need to, let's say, set the right context before testing the completion of some event, we can probably group we can group probably the posted events that we started according to the context and just switch between them. And then we will just do the minimal thing that we need anyway.
Most of that makes sense. Like Yossi, what I was thinking was when we have multi-context support, currently we only create streams and events assuming one context will ever be used. But every time we encounter a new context, we would have to replicate some of those resources.
Right.
And then when we go into progress path, we basically look up every context, and if it has any outstanding events on those contexts, and we'd have to progress all of those.
We should probably do it we should just have a list of all
active all events.
Not all contexts, but only contexts that have something on them.
If I understand right, like what you're saying is don't look up all contexts, but just keep a track of like all active events.
Right.
And whenever we try to progress any events, look up the associated context and set that context.
Right. And we can group them by context so we wouldn't switch every time.
Right. Yeah, that sounds promising enough an approach. We should talk about that again.
Okay. Any more questions?
Thank you, presenter. All right. So that was the last talk. That concludes the 9th annual UCF face-to-face. I hope everybody that attended virtually or in person was able to come away with something useful from this event. I hope those that attended in person enjoyed the venue. And apologies again for the technical difficulties at the start, but it got going pretty well. I think that's everything. I can't think of any other housekeeping things. I'm sure Pasha or Gilad will probably announce upcoming event schedule, and just keep an eye out for UCF news. I think that's everything. Have a good day, everyone.